Okay, so f doesn't have any repeated roots, so in its splitting field it has, well, as many as its degree roots. It has 2 roots. So f has 2 roots in K, 2 distinct, just to be clear, 2 distinct roots in K. Call them alpha and beta. So roots of f, let's say it's the set alpha and beta. Okay, so now this is a symmetric group on a set with 2 elements. Right, it's isomorphic to S2. To a symmetric group S2, how many elements does it have? Well, 2 factorial. It's got 2 elements, identity and the permutation that switches, that swaps alpha and beta. Right, so here now, the symmetric group on the set alpha beta, well, it's identity and the permutation, using the cycle notation from your group theory course, the permutation alpha beta. Right, this swaps alpha and beta. Transposition. Remember, so you have to remember the cycle notation from the group theory course for symmetric groups. So that's the symmetric groups on the set of roots of f. Okay, it's a group with 2 elements. Okay, so this Galois group, there's 2 possibilities now, right? It's either the trivial group, the trivial subgroup there, or it's the whole thing. Those are the 2 possibilities. So now, what did we learn about the number of elements of the Galois group of the splitting field? Remember this result is absolutely crucial. You have to remember it. If K is the splitting field of a polynomial f over f, where the irreducible factors of f are separable. Well, in this case, our polynomial f itself is irreducible and separable, so we're good. Then, so here and right here, f separable implies that the number of elements of the Galois group of the splitting field of f over f is equal to the degree of k over f. The fact that f is separable is absolutely crucial. So the number of elements of the Galois group is the degree of k over f. But what is that degree? The degree of k over f. So note that k is equal to f adjoint alpha. Why? Because, well, see, your polynomial f, it's a polynomial of degree 2. Remember, it's a polynomial of degree 2 with coefficients in f. Well, it has 1 root here, it has 1 root alpha here. So over this field, it's got 1 factor of degree 1, namely x minus alpha, right? And the polynomial f being of degree 2, but if it has 1 factor of degree 1, by the division algorithm, it will also have another factor of degree 1. It splits. So over this field already your polynomial splits, and then also k is forced to be just f alpha. Because f is not allowed to split over any smaller subfield of k. Well, so k is equal to f alpha, and then what's the degree of f alpha? So the degree of k over f, well, that's the degree of f alpha over f. Well, alpha is a root of an irreducible polynomial of degree 2. So this degree is 2. And this is because f is irreducible of degree 2. And f of alpha is 0. Okay, very good. So this degree of k over f is 2, and then so the Galois group, it has 2 elements. two elements. So it's a subgroup of order 2 of this group of order 2. So the Galois group is the entire symmetric group on the set of roots of F. So it follows that. So again, that the Galois group of K over F, so it has two elements. The number of elements is equal to the degree of K over F. So it has two elements and it's a subgroup of the symmetric group on two elements. Well, so it has to be the whole thing. So this is equal to the symmetric group on alpha beta. So the Galois group consists of two elements. There's one element of the identity map on K, and the other one is an automorphism that swaps alpha and beta. Okay, very good. And okay, so just to be clear here, okay, so the automorphism. So okay, so let's take this alpha beta. This is now an element in the Galois group of K over F. Well, when we think of the Galois group as a group of permutations of the roots of F, right? But okay, so can you give a formula for this element? Like a formula, if I give you an element of K, what's sigma of that element of K? Well, the formula is the following. K is F adjoint alpha, and so this being of degree 2, a basis over F for this field is given by just 1 and alpha. So you have to tell me, so an arbitrary element of K is something of the form A plus B alpha. Well, A and B are in F. This is any element of K can be uniquely written in this form, and then sigma of this will be, well, anything in F is sent to itself, so A plus B, and then alpha is sent to beta. So this is a formula for the automorphism of K, which swaps alpha and beta. Okay, let's summarize what we did. Suppose F is a field which doesn't have characteristic 2. Take a polynomial of degree 2 with coefficients in F which is irreducible. We saw that the Galois group of the splitting field of the polynomial over F is equal to the symmetric group on the set of roots of the polynomial. The polynomial will have two distinct roots, alpha, and let's call them alpha and beta, in the splitting field, and the Galois group will consist of two elements, one being the identity map, and the other one being the automorphism that swaps alpha and beta. So in another video, we're gonna now discuss. We're gonna think about cubic polynomials. But what I do want to say before we finish this video is that the hypothesis that the characteristic is not 2 in this picture is very important. If the characteristic is 2, then the derivative of your quadratic polynomial can actually become the 0 polynomial, right? If it's something of the form x squared plus a, and then you differentiate it, you're going to get the derivative will just be 0. If F is that, the derivative will just be 0 if the characteristic is 2. So if the characteristic is 2, your irreducible polynomial of degree 2 doesn't actually have to be separable. It can have repeated roots. And in that case, and in fact, actually, if you look back at, the last physical lecture that we had, remember we gave this example of an irreducible polynomial which wasn't separable? It was an example over the rational fields with coefficients in F2. Now, there you had a quadratic polynomial, irreducible quadratic polynomial, which actually had repeated roots. It really had just one distinct root in the splitting field, and it's a splitting field. And then in that case, the set of roots of it, well, it only has one element, so this is not a trivial group. And the Galois group will be also the trivial group. So just in short, this hypothesis that the characteristic is not 2 in this discussion is important because it guarantees that your irreducible quadratic polynomial has actually 2 distinct roots in a splitting field. Okay, thanks.